G'day. This is one of two worksheet videos on proofs of Pythagoras' theorem. This is about geometric proofs, and the other worksheet is about algebraic proofs. You may do these exercises on this worksheet, or you can use a geoboard. Doing them on a geoboard will make them easier to understand. I'm going to do them on both. Now, many of the geometric proofs use shearing as a way of moving polygons around, so I would like to just briefly go over shearing before we begin. Here, clearly, we have a rectangle. But if I were to shear that rectangle, it would become a parallelogram. If it has the same base and the same height, it has the same area. And this goes for any shear we would like to make. The green parallelogram has the same area as the orange and the original blue rectangle. Now I'd like to look at the red triangle, which is half the area of the rectangle. And if I shear the triangle, it is still half the area, it is still half the area, and it is still half the area. And now we can say that the red triangle is half the area of the blue parallelogram. Geometric proof number 1, which we're going to do by shearing squares. Now we wish to prove, of course, in each case, that a squared plus b squared equals c squared. I'll let the shortest side be a, so you can see we have the square on a and the square on b, and I'm going to form the square on c. To begin with, make a right triangle as above, and then make squares a squared and b squared on the two shorter sides. Shear both squares, keeping the same area, to the top left corner of the geoboard, forming two parallelograms. Well, I've done that, and this is still a squared, and this is still b squared. Now I'm going to draw another line. I see that the top triangle I've formed equals the original triangle. And if I were to translate that down into this space, then a squared plus b squared would equal c squared. Alternatively, if I were to shear the two parallelograms to a point on the top of c squared, they would form two rectangles, and a squared plus b squared would equal c squared. I'd like to do that now on the geoboard. We start with our right triangle in this position. So that would be side A, that would be side B, and this is side C. Now we shear both these squares to the top left corner of the geoboard. By putting another rubber band here, I form a right triangle in the top part of this figure, which is equal to this original right triangle. So if this triangle were to replace this one, then a squared plus b squared would in fact equal c squared. the second example, which is done by translating right triangles. In this example, it's important to think of the area inside the four right triangles, which are here, and the area outside that, which is, in the first picture, the area in the middle. And we're going to start moving these triangles around the geoboard. For our first move, we're going to move triangle T1 down 4 units and back 2 units so it meets triangle 3. So we're going to translate it down this way, like this. So it meets T3. Note that the area outside our 4 triangles still equals c squared. In step 3 here, we're asked to translate T4 up 2 units and then T2 across 4 units to here. And the area outside still equals c squared. But now we can see clearly that this area outside is a squared and b squared. And now I'm going to do it on the geoboard. We have our 4 right triangles. Triangle 1, 2, 3, and 4. And the area in the middle represents c squared. Our first move is to move triangle 1 down to meet triangle 3. Our next move is to translate triangle 4 up 2 units and finally to move triangle 2 across to meet triangle 4. The area outside our right triangles still equals c squared. Well, this is a squared and this is b squared. Geometric proof number 3. We're going to do this by rotating areas. We make a right triangle in the usual way. We call the shortest side A and make squares on the A side and the B side and on the C side. Now we're going to fill c squared with these other pieces outside c squared. So the first thing we do is rotate this triangle here down 90 degrees anti-clockwise so it fills this space here. Next, I've drawn an extra line here to divide this area in two, and I want to rotate this triangle 180 degrees so it fills this space here. Now what remains outside of a squared and b squared here is this space, and if I rotate this part of a squared 180 degrees, it will fill that space exactly. Now, all areas outside of c squared have been used. All parts of c squared are filled. Therefore, a squared plus b squared equals c squared. I'll now demonstrate that proof on the Geoboard. Here is our original right triangle, and we've built a square on the shortest side, A, another square on the middle side, B, and on the hypotenuse we have C squared. So the first thing I'm going to do is rotate this right triangle 90 degrees anti-clockwise down so it fills this space here. So then that disappears. Next, I'll make an extra line here, and then I'm going to rotate this small right triangle 180 degrees down to fill that space. So then that disappears. Now all I'm left with is this space here to fill. And I see that if I rotate this area of A squared 180 degrees, about this point, that it will fill that space exactly. So that disappears. All areas outside C squared have been used. All areas inside C squared have been filled. So now I can say A squared plus B squared equals C squared. Number 4, I've made Euclid's proof. Euclid lived about 300 BC, and he published a book called The Elements, in which was contained this proof and many others. This is fairly close to his original drawing. So we start with our original right triangle and build a square on A and a square on B and a square on the hypotenuse. Because this is a right angle, then this must be a straight line here, as this one must be. So then these will all be right angles. Drop a perpendicular from C down to its opposite side and keep going to the far side of C squared. I now wish to talk about this triangle here. I refer you to my earlier note about shearing at the beginning of the video. And if I were to shear this triangle to this point, it obviously would be half of this section of C squared. And if I were to shear the other triangle here to this point, together they would form half of C squared. If I were to rotate this triangle 90 degrees anti-clockwise, it would end up in this position. And if I were to rotate this triangle 90 degrees clockwise, it would end up in this position. But what Euclid does is he proves that each pair is congruent. I ask the question, is triangle KAB congruent to triangle CAE? Well, KA equals CA, KA equals CA, being sides of the same square, and AB equals AE, AB equals AE. They are also sides of the same square. Angle KAB equals angle CAE. Well, KAB, well, that is a right angle plus this interior angle of the original right triangle. And CAE is also a right angle plus the same angle of the original triangle. So they must be congruent. We have two triangles with two equal sides and an equal included angle. That is SAS, side angle side, they are congruent. Note that triangles KAB, this one, well, if this was sheared to this point, it's obvious this would be half b squared. In the same way, triangle HBA is congruent to triangle CBF by side angle side, and we note that triangle HBA, well, if that was sheared to this point, then it becomes obvious this is half of a squared. So we end up with half a squared plus half b squared equals half c squared. Therefore, a squared plus b squared equals c squared. I'd now like to show you that on the Geoboard. Note that I've had to add a clip here because I needed one extra nail to make b squared. This is our original triangle. So we have on one side a squared, on another b squared, and on the hypotenuse c squared. Just imagine I drop a perpendicular from this point down to touch this line at right angles. This divides c squared into two areas. Now I form two triangles from the point C, the orange one and the yellow one, and together they form half of c squared, because if both triangles were sheared to this point, it's obvious they would be half of c squared. Now I form two more triangles, the pink one and the bone-coloured one. Now the pink one could be a 90-degree anti-clockwise rotation of the orange triangle, and the bone triangle could be a 90-degree clockwise rotation of the yellow triangle, but I wish to prove they're congruent. And I can do that by SAS. This side equals this side equals this side, and this angle equals that angle, the angle being a right angle plus that interior angle of the original triangle in both cases. And the same goes for the triangle on this side. I can prove it is congruent by SAS. The next step is to realise that the bone triangle is half of a squared and the pink triangle is half of b squared. And if you're a bit unsure of that, by doing a simple shear, you can see it is the case. Now the bone triangle is obviously half of a squared, and the pink triangle is obviously half of b squared. So half of a squared plus half of b squared equals half of c squared. Okay, that's it for this worksheet. I have another video on the algebraic proofs of Pythagoras Theorem, which also has a worksheet. If you enjoy this video, you might enjoy that one too.